Okay, you know those old stories about alchemists? Like turning lead into gold?
Right, trying to change one element into another.
Yeah, and it turns out that part isn't completely fantasy.
Not magic, no. But elements can change. It's pretty wild, actually.
And that's what the sources for this deep dive get into.
Exactly.
How it happens.
Through radioactivity.
Which I gotta say is way cooler than magic.
Oh, yeah, definitely cooler. And what's really interesting is...
Go on.
It's not like mixing stuff up.
Like we did in chemistry class.
Right, exactly. This happens at the core of an atom in the nucleus.
Oh, so we're talking about changing what the element is.
Exactly, because the number of protons, that's what defines an element.
So to even understand how an element can transform, we got to start with radioactivity itself.
Okay, so...
It's when the atom's nucleus, that tiny center,
yeah.
It spits out these particles and energy.
And we call that energy radiation.
But it's not the same kind of radiation as, say, light from a lamp.
Right. It's a whole different ballgame.
Different kind of energy altogether.
It's like the atom, imagine it's trying to find its chill.
Okay.
That's kind of what radioactive decay is, in a way.
So, speaking of chill, let's rewind a bit.
Okay.
To how this whole thing was even discovered.
Back to the beginning.
Back to a scientist named Antoine-Henri Becquerel.
Ah, Becquerel.
Who was working with uranium.
Yeah.
And noticed that it kind of glowed after being in sunlight.
Okay.
So he leaves some in a drawer with a photographic plate.
Huh.
Doesn't think anything of it. But then later, when he develops the plate, boom.
What?
There's an image, even though it was in total darkness.
Talk about a happy accident.
Total X-Files stuff right there.
Really highlights how chance plays a role in science sometimes, right?
For sure. I mean, Becquerel's discovery, that paved the way for Marie Curie.
Curie, yeah.
Who not only gave us the term radioactivity, but, oh yeah, she also discovered two brand new elements, polonium and radium.
She was incredible.
A total rock star, especially for a woman in science back then.
Definitely ahead of her time.
Her work changed how we understand atoms, and that's had huge impact.
On everything.
From medicine to, well, this deep dive we're doing right now.
Absolutely.
Okay, so to really grasp these transformations, we need to talk about isotopes.
Okay.
Specifically, radioisotopes.
Right.
They're like variations of an element.
So, same number of protons, but different numbers of neutrons in the nucleus.
So, like carbon, we've got carbon-12, which is stable.
Right. The one we all know and love.
Yeah, but then there's carbon-14.
Which is radioactive.
So why are some isotopes radioactive and others not?
It all comes down to stability.
Okay.
You see, protons are positively charged.
Right. So they want to push each other away.
Exactly. And neutrons, those have no charge.
The peacekeepers.
Exactly. They help hold the nucleus together.
It's like a delicate balancing act.
It really is.
Yeah.
So small atom like carbon, it's happiest with...
equal number of protons and neutrons.
You got it. But as the atoms get bigger...
they need more neutrons to keep things from flying apart.
Yeah, it's like the bigger the atom, the harder it is to keep those protons in line.
Makes sense.
And actually, any element with more than 83 protons, it only exists in radioactive forms.
So it's like there's only so much you can do to keep those protons from repelling each other.
Exactly, exactly.
Okay, but here's something that's always tripped me up. We talk about radiation like it's this big scary thing.
Yeah.
But isn't it all around us?
Well, you're right. We're actually bathed in low levels of radiation all the time.
Really?
Yeah, it's called background radiation.
Okay.
And it comes from things like rocks, because some rocks contain uranium, which is radioactive, and even from space as cosmic rays.
Wow.
But the good news is this natural radiation, it's generally harmless.
Okay, that's reassuring. But there's a difference between background radiation and, say, the kind you'd find at a nuclear power plant, right?
Oh, absolutely. Absolutely. Yeah. It's all about the dose and the type of radiation. Okay. Background radiation is like a gentle hum, while concentrated sources can be more like a blaring siren.
Gotcha.
One example you might even encounter in your own home is radon gas.
Radon gas, okay.
Which forms from the decay of uranium in rocks and soil. And if it seeps into your basement, that's when it can become a health risk.
Makes sense. Okay, so now for the part that always sends chills down my spine.
All right.
The dangers of radiation. We can't see it, smell it, hear it coming. It's why those warning signs always creep me out.
Yeah, true. It's a bit of a stealthy foe.
It really is.
And the reason it's dangerous is because it can knock electrons off atoms, creating ions.
Right.
And this process, it's called ionization, it can mess with the delicate machinery of living cells.
Oh, so that's how it causes damage.
Right, damaging DNA and other important molecules. And the effects depend on how much radiation you're exposed to and for how long.
So a big dose all at once, that's obviously bad news.
Yeah.
But even low levels over a long time can be risky.
Exactly. A sudden high dose that can cause burns, radiation sickness with fatigue, hair loss,
Yikes.
not pretty, and prolonged low-level exposure, like from that radon we talked about,
Right.
that increases the risk of cancer.
And sadly, Marie Curie herself died from cancer.
Yeah.
Probably due to all those years working with radioactive materials.
Yeah, it's a reminder that even though we can't sense it, radiation is a powerful force.
It's amazing how something we can't even see can be so impactful. So if we can't sense it, how do we know it's even there?
That's where our friend the Geiger counter comes in.
Ah, the Geiger counter, like a sixth sense for radiation.
Exactly. Inside there's a tube filled with gas. When radiation enters, it ionizes the gas, creates a tiny electrical current,
Okay.
and that triggers those clicks you hear.
The faster the clicks, the more radiation.
You got it.
So radiation can be dangerous, but it's also got some pretty amazing uses, right? Like we use it to figure out how old dinosaur bones are.
Yeah, it's kind of like having superpowers. We use it for dating ancient artifacts, yes, but also in medicine, especially for cancer.
Oh, right.
And of course, there's the whole realm of nuclear energy.
Well, before we get to harnessing the power of the atom, I'm really curious about how radiation helps us date stuff. I mean, how can something invisible tell us how old a fossil is?
Well, that's where the different types of radioactive decay come in. Each element has its own unique decay fingerprint.
Okay.
And just like fingerprints can identify a person,
Yeah.
these decay signatures can help us identify different elements and figure out how long they've been around.
Okay, that sounds intriguing. We're diving deeper into types of decay next.
All right. But first, let's take a quick detour into the medical world
Right.
and see how something that can be so harmful can also be used to heal.
This is where I think things get really interesting.
Oh, you're right. This is where the story of radiation takes a truly remarkable turn. And it all starts with understanding how we can manipulate these radioactive processes to our advantage. Yeah, it's like we're turning a villain into a superhero.
Okay.
Take radioactive glucose, for example.
Okay.
It's used to target and image cancer cells.
Interesting.
Because cancer cells are hungry for energy, they gobble up this glucose, and since it's radioactive, we can track them, see where the cancer is hiding.
Wow, so it's like a radioactive beacon leading us straight to the enemy.
Oh, exactly.
And I've heard about radiation being used to actually destroy cancer cells, too.
You're exactly right. That's radiation therapy.
Okay.
We can use targeted beams of radiation to zap those cancerous cells,
Wow.
while hopefully sparing the healthy ones nearby. It's a powerful weapon in the fight against cancer.
It really is remarkable how we can harness something so potentially harmful for good. It reminds me of those old kung fu movies.
Yeah,
They say the best way to defeat your enemy is to turn their strength against them.
I like that.
Okay, so now I'm ready to dive into those different types of radioactive decay you mentioned earlier. I'm guessing this is key to understanding how we can use radiation for things like dating artifacts.
Absolutely. Think of it this way. Each radioactive element has its own unique decay signature,
Okay.
kind of like a fingerprint.
Okay.
And just like fingerprints can identify a person, these decay signatures can help us identify different elements and figure out how long they've been around.
All right, lay it on me. What are these different types of decay?
There are three main ones to know: alpha, beta, and gamma decay.
Okay, 3.
They each involve the nucleus spitting out different types of radiation, each with its own level of penetrating power.
Ooh, penetrating power. That sounds intense. So some types of radiation are more dangerous than others.
Exactly. Alpha decay is like a heavyweight boxer who throws a powerful but short-range punch.
Okay.
It involves the release of an alpha particle, which is essentially a helium nucleus. 2 protons and 2 neutrons bundled together.
Okay, so it's a chunk of the atom's core being ejected. Got it. But you said short-range punch.
Right. Alpha particles, they're big and heavy, so they don't travel very far, and can be stopped by something as thin as a sheet of paper or even your skin.
Oh, wow.
They can cause burns on the surface, but don't penetrate deeply.
So that's why alpha radiation is less of a concern unless you ingest or inhale a source, right?
Precisely. Now, beta decay is more like a lightweight fighter who throws a flurry of jabs.
Okay.
It involves the release of a beta particle, which is simply an electron.
Wait, an electron? I thought those were outside the nucleus zipping around.
Good catch. In beta decay, a neutron in the nucleus transforms into a proton and an electron. The
Okay.
proton stays put, but the electron gets ejected as the beta particle.
Aha. So that's how the element actually transforms. You're changing the number of protons in the nucleus.
Exactly.
And you mentioned beta particles travel farther than alpha particles.
You got it. Beta particles are lighter and can penetrate further, requiring something like aluminum foil to stop them.
Oh, okay.
They can penetrate skin and cause damage to living tissues.
So beta radiation is a bit more of a concern than alpha. And what about this gamma decay? What's that like?
Well, gamma decay is different. Think of it as a stealthy ninja warrior.
Okay.
Instead of throwing particles, it releases pure energy in the form of gamma rays.
Gamma rays. Those sound familiar. Aren't they like superpowered X-rays?
You could say that. Gamma rays are electromagnetic radiation, similar to light and X-rays, but with much higher energy. And unlike alpha and beta decay, gamma decay doesn't change the element itself. It's often like a bonus round accompanying alpha or beta decay.
Okay, so gamma rays are pure energy, not particles.
Yeah.
That's why they can penetrate so deeply, right?
You're right on the mark. Gamma rays are the most penetrating of the three. They can zip right through your body and require thick lead or concrete to stop them.
Wow.
That's why shielding against gamma radiation is so important in places like hospitals and nuclear power plants.
So it's like a radiation spectrum. Alpha is the close-range fighter, beta is the mid-range jabber, and gamma is the long-range sniper. Makes sense.
That's a great analogy. Now, to really understand how we use these different types of radiation for things like dating, we need to talk about another key concept: half-life.
Ooh, half-life. That's one I've heard before but never fully grasped. It has something to do with how fast radioactive elements decay, right?
Exactly. Every radioactive element has a characteristic half-life. It's the time it takes for half of a given sample of that element to decay. Think of it like a radioactive clock ticking away at a specific rate.
Okay, I'm starting to get it. So some elements have a short half-life, meaning they decay quickly, and others have a long half-life, meaning they decay slowly.
You're getting it. And here's where it gets really interesting. We can use those half-lives, those radioactive clocks, to figure out how old things are. It's like having a time machine.
Whoa, wait, explain that. How can knowing how fast something decays tell us how old a dinosaur fossil is?
Okay, imagine you have a fresh batch of cookies. Every hour, you eat exactly half of what's left.
Okay.
So you start with 100 cookies, an hour later you have 50, an hour after that you have 25, and so on. Now, if I came in and saw only 12 cookies left, I could work backward and figure out how long ago you baked those cookies.
Okay,
Yeah.
see the analogy. So with radioactive elements, we're not eating cookies,
Right.
but we're watching how much of the original element is left
Exactly.
after a certain amount of time has passed.
And because we know the half-life of different elements,
Right.
how long it takes for half of them to decay, we can calculate how long it's been since they were formed or since they were part of a living organism.
Wow, that's incredible. It's like each radioactive element has its own unique timer built in.
Yeah.
So what about carbon dating? How does that work?
That's a great example. Carbon-14 is a radioactive isotope of carbon with a half-life of about 5,730 years. It's constantly forming in the atmosphere and gets incorporated into living things. When an organism dies, it stops taking in carbon-14, and the carbon-14 it already contains starts to decay.
So by measuring how much carbon-14 is left in a fossil, we can work backward and figure out when that organism died. That's amazing. But what about really, really old things like dinosaur bones? Carbon-14 wouldn't work for that, right?
You're sharp. For things older than about 50,000 years, we need to use elements with longer half-lives. For really ancient stuff, like rocks billions of years old, we might use uranium-238, which has a half-life of over 4 billion years.
It's like having a whole toolbox of radioactive clocks, each one suited for a different timescale.
You got it. Now, with a better grasp of radioactive decay types and half-life, we can delve deeper into the world of nuclear energy, where the incredible power locked within the atom is both a blessing and a curse.
Okay, let's unleash the power of the atom. But before we do, can we take a quick step back? I feel like we've been talking about radiation a lot, but I'm wondering, how does all this connect to nuclear energy? Is it just about harnessing that radiation somehow?
That's a great question. And the answer is kind of, but not exactly. The key to nuclear energy is understanding that while radiation is a byproduct,
Okay.
the real power comes from the processes happening within the nucleus itself.
Okay.
There are two main ways we harness this power: nuclear fission and nuclear fusion.
Fission and fusion, I remember those terms. Fission is splitting atoms and fusion is smashing them together, right?
Yeah.
But how does that actually release energy?
You're on the right track. It all boils down to EMC2, that famous equation from Einstein.
Hold on. Einstein's involved in this too. I'm sensing this is about to get mind-blowing.
You're not wrong. EMC2 tells us that mass and energy are actually two sides of the same coin. They can be converted into each other, and that's the key to understanding the immense power of nuclear reactions.
Okay, I'm buckled up and ready for the ride. Explain it to me like I'm 5. How does EMC2 relate to splitting or smashing atoms?
All right, let's break it down. In both fission and fusion, we're essentially rearranging the building blocks of atoms, protons and neutrons.
Okay.
And what's amazing is that when we do this, a tiny amount of mass actually disappears.
What?
It doesn't just vanish into thin air. It gets converted into a huge amount of energy, according to Einstein's equation.
Wait, so you're telling me that by rearranging tiny particles inside an atom, we can unleash enough energy to power cities?
Exactly. It's almost like alchemy, but instead of turning lead into gold, we're turning a tiny bit of mass into a tremendous amount of energy.
Wow, that's incredible. Okay, so I get the big picture, but I need some details. Let's start with fission. How does splitting an atom actually release energy?
Imagine you have a heavy atom like uranium-235. If you hit it with a neutron, it's like throwing a match into a fireworks factory. The uranium nucleus splits into smaller atoms, releasing a tremendous amount of energy and more neutrons in the process.
Yep.
Those released neutrons can then go on to split other uranium atoms, triggering a chain reaction.
A chain reaction, so it's like a domino effect of atoms splitting and releasing energy.
Exactly.
But that sounds a bit dangerous, doesn't it? Like, how do we control that?
You're absolutely right. Controlling that chain reaction is the key to harnessing nuclear fission for peaceful purposes. In nuclear power plants, we use materials called control rods to absorb some of those extra neutrons, preventing the chain reaction from running out of control.
Okay, that makes sense.
Yeah.
So we're basically taming a nuclear chain reaction to generate electricity. It's a powerful source of energy, but I know it's not without its risks, right?
You're sharp. While nuclear fission offers a lot of potential benefit, it's also a powerful technology that needs to be handled with extreme care. And that's where the ethical considerations come in.
Right.
We can't talk about nuclear energy without acknowledging the serious risks and responsibilities that come with it.
Okay, let's get into that. What are some of the biggest ethical challenges we face with nuclear fission?
Well, one of the most pressing concerns is the potential for accidents. History has shown us that even with the most advanced safety measures, nuclear accidents can and do happen. Events like Chernobyl and Fukushima are stark reminders of the devastating consequences that can result from even a single misstep.
Right. Those events were tragic
Yeah.
and really highlighted the potential dangers of nuclear power. And what about the waste? I know that's a big concern too, right?
Absolutely. Nuclear fission produces radioactive waste that can remain dangerous for thousands of years.
Wow, thousands of years. So what do we do with it? I've heard it's a real challenge to store it safely.
It is. Finding safe and secure long-term storage solutions for nuclear waste is a huge challenge.
Yeah.
And it's something we have to get right. We need to ensure that this waste doesn't pose a threat to human health or the environment for generations to come.
It makes you think about the long-term implications of our actions, doesn't it? We have to be responsible stewards of this powerful technology. Okay, so we've talked about the risks of fission. What about fusion? Is that a safer alternative?
Fusion has a lot of potential advantages over fission
Okay.
in terms of safety and waste. It's the process that powers the sun and other stars,
Right.
and it involves fusing light atoms like hydrogen isotopes to create helium, releasing even more energy than fission.
Fusion sounds amazing. No radioactive waste, and we have a virtually unlimited supply of hydrogen in seawater. So what's the catch? It sounds too good to be true.
Well, the catch is that fusion requires incredibly high temperatures and pressures, millions of degrees Celsius, to overcome the repulsion between the positively charged nuclei. We're talking about conditions similar to the core of the sun.
Wow, that's hot. So we can achieve fusion in labs, but it takes a lot of energy to create those conditions, right?
Exactly. While we've made great strides in fusion research, we're still a long way from achieving sustained and controlled fusion reactions that can produce more energy than they consume. It's a bit like trying to bottle up the power of the sun.
It sounds like an incredibly challenging task, but also an incredibly exciting one. If we can crack the code of fusion, it could revolutionize energy production as we know it.
You're right. It's a frontier of science with incredible potential. And while the technical challenges are immense, the potential rewards are equally vast. Imagine a future powered by clean, safe, and nearly limitless energy from fusion.
That's a future I can get behind. But for now, It seems like fission remains a key player in the global energy landscape, despite its challenges. So I'm curious, knowing what we know about the risks and the potential benefits, what role do you think nuclear energy should play in our future?
That's a complex question with no easy answers. It's a question that societies around the world are grappling with right now.
It's a question that requires careful consideration of scientific, economic, environmental, and ethical factors, wouldn't you say?
Absolutely. We need to weigh the risks and benefits, the short-term and long-term consequences, consider the full spectrum of alternatives. It's a discussion that needs to involve scientists, policymakers, industry leaders, and citizens alike. We all have a stake in shaping a sustainable and ethical energy future.
I couldn't agree more. Speaking of ethics, we've talked about the ethical challenges of nuclear energy, but there's another ethical dimension to nuclear technology that we can't ignore, and that's the existence of nuclear weapons.
You're right. The development of nuclear weapons marked a turning point in human history. For the first time, we possess the ability to destroy ourselves many times over. It's a sobering reality that casts a long shadow over our world.
It's a responsibility that weighs heavily on humanity.
It does. The threat of nuclear war is a constant reminder of the fragility of peace and the urgent need for global cooperation. It's a reminder that the choices we make today have consequences that extend far beyond our lifetimes.
It's a lot to consider, but these are conversations we need to have. So I'm curious, knowing what we know about the destructive power of nuclear weapons, how do we navigate the ethics of nuclear technology in a way that prioritizes peace and safety for all?
That's the million-dollar question, isn't it? It really is. It demands a multifaceted approach, one that involves diplomacy, disarmament efforts, non-proliferation treaties, and fostering a global culture of peace and understanding.
That's a tall order for sure, but it sounds like it all boils down to responsible leadership and international cooperation, right?
You nailed it. We need leaders who understand the gravity of the nuclear threat and are committed to working together to reduce the risks. We need to prioritize dialogue over confrontation, find common ground in our shared humanity.
It's a reminder that peace is not just the absence of war. It's an ongoing process that requires constant effort and vigilance.
Well said. It's about building bridges, fostering trust, and recognizing our interconnectedness. We all share this planet, and we all have a stake in ensuring its survival.
Okay, so we've covered a lot of ground in this deep dive. From the accidental discovery of radioactivity to the mind-boggling power of nuclear reactions and the ethical challenges we face in harnessing this power responsibly.
It's been quite a journey, and it all stems from the incredible power contained within the atom, a power that can be both awe-inspiring and terrifying.
I have to say, it's been a real eye-opener for me. I'm walking away with a newfound appreciation for the complexities of this subject.
I'm glad to hear that. Knowledge is power, as they say. And the more we understand about these powerful forces, the better equipped we are to make informed decisions about our future.
Speaking of knowledge, is there anything in your research that really surprised you?
You know, one thing that always fascinates me is the concept of mass energy equivalence, that idea that mass can be converted into energy and vice versa. It's such a fundamental concept, yet it's so mind-bending.
Right, EMC2. It's more than just a cool equation on a t-shirt. It's a profound statement about the nature of reality itself.
It really is, and it has such profound implications for how we understand nuclear reactions. It explains why such incredible amounts of energy are released in processes like fission and fusion.
It's like the universe is playing a cosmic game of energy hide and seek, and EMC2 is the key to unlocking the secret. Okay, so before we wrap things up, is there anything else you think our listeners should know as they continue to explore this topic? Any key takeaways or food for thought?
Well, I think it's important to remember that while nuclear technology poses risks, it also offers incredible opportunities. It has the potential to provide clean energy, advance medical treatments, and help us unlock the secrets of the universe.
It's a reminder that technology itself is neither good nor bad. It's how we choose to use it that matters.
Exactly. It's up to us to ensure that we use our knowledge wisely and ethically to create a better future for ourselves and generations to come.
Well said. It's been a fascinating and thought-provoking deep dive, and I want to thank you for being such a fantastic guide through this complex landscape.
It's been my pleasure.
And to our listener out there, I encourage you to keep exploring, keep questioning, and keep learning. The world of radioactivity and nuclear reactions is full of wonder and possibility, and who knows, maybe someday you'll be the one making groundbreaking discoveries in this field.